to have a look at trends in the periodic table in this video. So the first thing that you need to know about is the trend in atomic radius. So I suppose we need to firstly consider, what does atomic radius mean? So if you think about the radius of an atom, you might think, well, this is the nucleus in the center and this is the outermost electron. So I'm looking at the distance between the nucleus and the outermost electron. That would be the radius of the atom. The only problem is Heisenberg said that it is impossible to measure at the same time the position and the velocity. So where is the outer border for an atom? Or in other words, where is the outer electron for the atom? We don't know, okay? So what they do to get around this is they use X-ray diffraction to measure the distance between the nucleus of two covalently bonded atoms. So say, for instance, this could be oxygen. This is the nucleus of oxygen here in the center, the nucleus of the second oxygen atom. So this is an oxygen molecule here. Okay, so you have two oxygen atoms covalently bonded together. The X-ray diffraction will measure the distance between the two nuclei. Okay, and then how do we get the radius? We halve that distance. Okay, so there's a definition of atomic radius of an atom is defined as half the distance between the nuclei of two atoms of the same element that are joined together by a single covalent bond, okay? As before we talk about the trends in atomic radius, I'm just going to quickly run through again the structure of an atom. So you know that in the nucleus you've got the protons, and you know that protons are positively charged. So when I talk in a minute about nuclear charge, I am talking about the charge of the nucleus being positively charged, because what else is in the nucleus? Neutrons. They don't have any charge. So that nucleus here has the protons inside in it, and it's the protons that are positively charged, and those protons will exert a force of attraction on the electrons that are traveling around in the shells or energy levels. Okay, so you have a positive charge in here. We know that the electrons are negatively charged, so there's a force of attraction there between the nucleus and the electrons. Now, if you've got lots of shells of electrons in between the nucleus and the outermost electron, then those electrons in the intervening shells are going to kind of block the force of attraction that the nucleus has for the outermost electron. And that phenomenon is known as shielding or screening. So just to run through that again, if there's lots of electrons in between the nucleus and the outermost electron, then those electrons in the middle, in between, will try to block or shield or screen the positive force of the nucleus in attracting the outermost negative electron, okay? Now, if I was in school, the way we would do this is we'd have a sheet of paper, so you could do this at home now as well. Get out an A3 sheet or A4, whatever you have, and I would say to you, okay, we're going to draw atoms of sodium, lithium and potassium. And if you look up in your periodic table, you see that lithium is 3 and 7. You see that sodium is 11 and 23, and you'll see that potassium's nuclear formula is 19 and 39. Now, I'm just going to really quickly draw lithium here for a second. So you can see in the nucleus, you're going to put 3 protons, because 3 is the atomic number, 4 neutrons. Now, the neutrons aren't going to affect it really, remember, because they're not charged. In the first shell, I can put in 2 electrons, remember, and then in the next, n equals 2. I can put in another electron. So the configuration there for lithium then would be 2 equal, Li equals 2, comma 1, okay? I'm not going to draw sodium, but you can draw sodium yourselves, okay? And now, what you should be doing really is pausing the video, drawing the 3 atoms underneath each other. So if I attempt to draw potassium, but I'm going to run out of space, 19 protons, 20 neutrons, and then I have to go, okay, 2 in the first shell, I'd have to put 8, and 1. So the configuration for potassium would be 2, 8, 8, 1, and that would be 2 and 8 is 10, and 8 is 18, and 1 for 19 electrons that I would need to put in. So you do that going down your sheet of A4 paper, and what do you notice straight away about the atomic radius, the radius of the atoms? Well, clearly the radius is increasing as you go down a group. So they'll ask you for the trend. They might ask you for the general trend in atomic radius as you go down a group, and you will say the general trend is that the radius increases. Now you have to be able to explain why, okay? So why is the radius increasing as you go down? Well, you can clearly see that you're adding a new level. You're adding a new shell. You're adding a new energy level. main energy level. So that's N equals, that's the nucleus in here. So this is N equals 1, N equals 2, N equals 3, N equals 4. So a new energy level is being added each time. And the other thing is that this is your electron out here. This is the positive force of the nucleus in here. Look at all the screening or shielding that's going on between the nucleus and the outermost electron, because that positive force should attract the electron, the negative electron in, which would try to tighten up or try to make the atom smaller. But because of all the screening or shielding in between, in the middle, it's not able to do that. So 2 reasons why atomic radius increases as you go down the group, because you're adding a new energy level. Okay, and the second reason is because you've got increased screening or increased shielding. Now, the other thing I just want to look at there then is you might be asked as you go across a period. So down a group we've dealt with. Now, what about across a period? Now, again, at home, you should be pausing this video and you should be drawing out on your sheet paper. You've drawn lithium already, okay? So you could be drawing boron. Boron is 5 and 10. Oxygen is 8 and 16. Neon is 10 and 20. So, and we had earlier on there that the lithium was 7 and 3. So if I just quickly redraw lithium here, okay, and you're putting the 4 neutrons at the first shell, 2, and in the next energy level you're putting 1. So Li equals 2, comma 1. Now you draw boron and oxygen yourself because I don't have room here, but I'm just going to draw, so it's neon there, 10 protons, 2 electrons in the first shell, and then you're drawing the next shell, 1, 2, 3, 4, 5, 6, 7, 8. Now, what do you notice there now as you're going across a period in the table? So the first thing you notice is that you're not introducing a new level. You're not introducing a new energy level. The electrons are going into the same energy level. So, right, this is your energy level 1, this is your energy level 2. 1, 2. So you're not introducing a new level, but what you are doing is you're increasing hugely the number of protons. So this nucleus here has a much greater positive force because of the extra protons that it has. So its nuclear charge is increasing. That's the way it's written, okay? So the nuclear charge is increasing because you're adding in more protons. And the other thing, lads, is because you're not adding a new energy level, there is no increase in screening or shielding. So there are no electrons in the middle getting in the way, blocking the positive force of the nucleus. So what can this neon nucleus do? Well, it can attract in the outermost electrons, making your atom smaller. So your general trend as you go across the period is that the atomic radius decreases. Why? Because you've got an increasing nuclear charge, because you're adding in more protons into the nucleus, but without an increase in screening, because they're all the electrons are going into the same shell. And what we consider that to be is an increasing effective nuclear charge. That kind of incorporates both points, that there's no screening increase and that there is an increase in nuclear charge. So the effective nuclear charge is increasing as you go across, and that's why the atomic radius will decrease. Now, I just very quickly want to have a quick look now at the trends in electronegativity values. Now, you already have drawn the atoms going down the group. You already have your lithium, sodium, potassium drawn, and you already have your lithium, boron, oxygen and neon drawn in your sheet. So you can easily now just kind of put alongside atomic radius, you can put in electronegativity trends. So what do you think would happen to the electronegativity values as you go down a group? Now, you firstly need to consider again, what does electronegativity mean? Well, electronegativity is the relative attraction that an atom has for what? For a shared pair of electrons. So lads, where would the shared electrons be? They would be in the outermost shells. So you need to consider what would the attraction of the nucleus of the atoms be for the outermost electrons, because that's what they're trying to pull. So think of the tug of war analogy that we used in school, where you have the nucleus trying to pull the outermost electrons. So what do you think now? Look at your atoms of lithium, sodium, potassium. As you go down the group, do you think it would be easier for, or maybe not easier, but do you think that potassium would have a greater attraction for the outermost electron, or would lithium have a better attraction or a stronger attraction for the outermost electron? So you need to consider that. So obviously it would be lithium. Why would lithium have a greater attraction or a greater pull for the outermost electron? Well, the first thing is the radius of lithium is smaller, so the nucleus of lithium is closer to the outermost electron, whereas if you look at potassium, the nucleus is physically much further away from the outermost electron, so lithium would have a greater attraction for that electron because it's closer to it, okay? The other effect then, or thing, of course, is that as you go down the group, the screening or the shielding is increasing. So what are the intervening shells of electrons doing to the outermost electron? In potassium, they're stopping the potassium's nucleus being able to attract that outermost electron. So as you go down the group, electronegativity values will decrease. Why? Because the radius of the atoms is increasing and there's an increase in screening or in shielding. As you go across the period, what happens to electronegativity values? Well, those values will increase. Why will neon have a greater attraction or a greater pull for the outermost electron? Well, firstly, because the atom of neon is smaller than an atom of oxygen, boron or lithium. So the outermost electron is closer to the nucleus of neon. And there's no increase in screening, remember, because you're not introducing new energy levels. They're all of the electrons are going to the same energy level, n equals 2. And so there's no increase in effective nuclear charge. Okay, so you're going to say those are your two reasons. So the electronegativity value going across a period will increase. Why? Because the atomic radius of neon is decreasing. Why is the atomic radius of neon decreasing? Because you have more protons in the nucleus, so you have a greater nuclear charge and you have no increase in screening. So the nucleus of neon will be able to keep or pull the outermost electrons closer to it, therefore having a higher electronegativity value.